Hi, I just wanted to show a quick exercise from Advanced Linear Algebra by Stephen Roman. Assume that R is a commutative ring with identity, and that every R module is free. Show that R is in fact a field. So, how we're going to do this is first we can show that R is actually a domain, and then with that we can use the properties of module homomorphisms, in fact linearity, to show that R is a field. So, first we want to show that R is a domain. How we can do that is we can do a proof by contradiction. So assume that R is not a domain. So we can assume that R has a zero divisor. So we assume there exists some x in the ring such that its annihilator is non-zero. It follows that the annihilator of x is actually an ideal of R, and it's also the ideals of R are submodules when we consider R as an R module. So that means that this is actually, from our assumption, isomorphic to R to the n, but R to the n actually can't be a torsion module, whereas this annihilator is, because x annihilates everything in here by definition. And on this right hand side we have 1n, right? The multiplicative identity on Rn. But for any for anything in Rn, 1n is just going to return it. So the only element in Rn that returns 0 and multiplied by 1n is going to be like 0 itself. So LHS is torsion. RHS is not torsion, so that's a very easy proof by contradiction. Now, we get R as a domain. Now, we actually want to show that R is a field. So how we're going to do this is we have that R is a domain, so we can use the property that if we multiply two things together that are non-zero, then we're going to get something non-zero. Now, we know that a ring is in fact a field if all of its, or a commutative ring of one, if all of its ideals are trivial, so it only has one ideal being the zero ideal. So, we're going to assume again for contradiction that there exists some non-zero ideal I, such that I is not equal to 0. Then we're going to let x be an I. Now, we can consider R mod I as an R module, and from our original assumption, we again get R mod I is isomorphic to R to the m for some m. Let's call this isomorphism phi. Now, if we have x times phi of 1 equals phi of x equals phi of 0 equals 0 for this x in the ideal, because obviously x on this side of the map is in the ideal, so it's in the quotient, so it's 0. And on this side, we have, in R to the m, x times phi of 1, and this has to be 0. So either x is 0, or we have that phi of 1 is 0. However, we know that x is not 0 by our assumption, so we get, but since phi of 1 determines the R module isomorphism, we actually get that R mod I is isomorphic to R to the 0, so m equals 0. And this means that we're done because that implies that I equals R. So the only ideal that R has not equal to 0 is R itself. So R must be a field.